Thanks very much. Hi, everybody. It's good to see everyone here. I was going to say that, so I'm in Canada, and I was going to start by saying that it's so nice that I could come to a BayesiaLab conference without having to bring my passport. But it seems like nobody had to bring their passport this year just because of the way things are. But next year, we look forward to welcoming you to Toronto. I'm not in Eastern Canada. I'm on the West Coast. So I had a very early start today, dark and early start to my morning. So I asked Stefan specifically not to schedule my talk so early. So he indulged me. What I'm going to talk about for those of you who don't know me is I'm a biologist. So I've been applying Bayesian networks for some number of years to the systems in which I work. And I've talked to the issue of the Woodland Caribou system. And that's going to be speaking to today. I'm looking at you, so I'm not looking at my screen. So I'm going to assume that everything is zooming okay here. But I wanted to start by talking about my collaborators on this project. So that's me on the left with the glasses on, and beside me is Dr. Tom Nuds. He's a retired professor from the University of Guelph. So he's helping out on that project. And then the guy on the horse is Andrew DeVries. He works for Tolko Industries, which is a forest company here in British Columbia. And just want to acknowledge that they have been funding this project on an ongoing basis and really support. We're super happy that they're supporting this work. I'm just going to give you a bit of background around the Woodland Caribou system. I skipped a slide here, just a sec. Caribou are a fairly iconic species in Canada. For any of those of you who have ever seen a Canadian quarter, well, maybe you don't realize, but the Woodland Caribou is actually on the Canadian quarter. And it's a species that's fairly widespread in Canada. I have this nice graphic of populations and their distribution everywhere. The big circles, I don't know if you can see my mouse or not, but the big circles, the big gray circles are the historic populations. And then the smaller circles are the current populations. And I don't want you to spend too much time on the blue of this map, but you can see the distribution of the green and the red and the purples. And that's the distribution that I'm talking about today. When people think about caribou, they often think about the big herds traveling across the Arctic tundra in the north. And that's what those blue and purple areas, those are the caribou in that area. But I'm talking about the caribou that range farther south in those green and red areas. And as you can see, this is from a trail camera, that they're actually fairly solitary. They move in small groups in fully wooded areas. I talked about trail cameras at the, I think that was the Chicago conference. A great way now of collecting information on animals in a non-invasive way. So the interesting thing about caribou in this caribou decline that we're seeing in Canada is that it's part of really a circumpolar decline of the species. So you can see from this map, just looking down on the world, you can see all the red ranges. Those are all the places where caribou are declining. The green ones are where they're increasing. So very few places are they increasing. Caribou, the species is circumpolar. So reindeer in Europe is the same and Asia is the same as caribou in Canada. They're actually the same species, exactly the same species, but they just go by different names. So in Europe, the name is reindeer. Rein is from the Old Norse word rein, and then deer actually comes from der, Middle English, which just means wild animal. And then caribou is derived from the Mi'kmaq word, which is one of Canada's First Nations. It came to us through the Mi'kmaq language via French settlers. So that's why we call them caribou in North America and reindeer in Europe. But yeah, as you can see from here, they're declining pretty much everywhere. And what I find really fascinating about this is that this is happening in countries that have obviously very strong environmental traditions. We think of Sweden and Norway, Finland, Canada, the United States, Russia, who knows, but certainly lots of places with strong legacies of endangered species protection, habitat protection. And yet we still can't seem to crack the nut on how to improve things for caribou. This is a true conservation challenge that a lot of effort is going towards trying to figure out what's going on here. So let's talk a little bit about what's causing the decline. And to do that, we have to dig into the system. So this is an illustration that we did a few years ago to try to explain what we think is going on from a big picture here. At the very top end, what we have are is basically situations related to habitat change. So we have situations where we have a warming climate, obviously, which creates forest fires. And that warming climate and forest fires basically is shifting the age structure of our forests younger. And younger forests produce a lot more forage. And species like elk, moose, and deer benefit very much from that forage. They also benefit from the warmer climate because they can survive the winter better. So as the climate warms, and also just in terms of the current climate going from south to north, warmer in the south, colder in the north, obviously, these animals, elk, moose, and deer, do much better at the southern end of their range than they do up at the north end. And so as these populations start to build, and we can contribute also to that habitat change by logging as well. So that's the other major habitat change that encourages populations of elk, moose, and as these populations build, wolves start to move in. So wolves are the major predator of moose, elk, and deer. And so as those prey populations go up, the wolves respond as well. And then the wolves chase the caribou and cause the caribou declines. And because caribou have fewer babies than moose, deer, and elk, then the caribou always tend to lose in this equation, and they're being driven to very low levels. There's one other mechanism that's going on here, and that is other kinds of changes where we're putting what we call linear features on the landscape. So this might be seismic lines that are associated with oil and gas exploration and development, could be roads, corridors, etc. And these linear features on the landscape basically serve as travel corridors for wolves. And they allow the wolves to travel farther and faster, and again, just increase pressure on the caribou. So it's a fairly complex system. There's indirect mechanisms going on here, moving from ultimate habitat change mediated through this predator-prey relationship, and then the caribou decline. So it's a fairly long and indirect route. In the past, of course, all we did was protect habitat. It used to be to the point where if you wanted to protect a species, make sure that it persisted on the land base, we could establish protected areas where natural ecological processes continue, and then we would be okay. But the really interesting thing here is that even in our large protected areas in Canada, we're starting to lose this species. Jasper National Park is probably Canada's second most famous national park next to Banff. Banff and Jasper together cover an area twice the size of Yellowstone. So we're talking about a substantial protected area network. There's also other protected areas that are linked to those, which creates a huge area along the spine of the Rocky Mountains through Canada. But caribou have been extirpated from Banff National Park, and they're on their way out in Jasper National Park. So even at this very top end, where we have these very large protected areas, we're still losing this species. And this has forced us to take fairly drastic action and try some other kinds of actions. So for instance, we have started doing what we call maternity penning in some places. And so this is a female caribou and her calf, and you can see that there's a geotextile fence behind her. And so what in places we've done is build these pens out in the bush, basically, maybe 10 hectares or so. And then we bring the females in when they're pregnant, bring them into this enclosure and let them calve inside the fence and keep them there for about 30 days before releasing them back out into the wild. And what this does is protect the calves from the very early predation that can come when they're very young. So about 50% of calves are lost to predation in that first 30 days. You can hold the calves and the mothers in the pen for 30 days. The hope is that we can get past this initial flush of predation and then increase their subsequent survival. But you can imagine that this is a very expensive process. You have to build these enclosures. You have to staff them in the bush. So we're talking about remote sites with generators. You have to go out into the field and capture the females, bring them into the pen, It's disruptive to wildlife populations, expensive to conduct. So it's more intensive than we really want to be. The other thing that we're trying to do is looking at trying to restore habitat. And I know this looks like we're making a giant mess here, but what happens is on some of these linear features, you get stagnation because of soil compaction and changes in the hydrological flow of water through these areas. And so you have to basically go in there and make a bit of a mess to start the process of allowing vegetation to grow back on these sites. But again, very invasive, very expensive. These machines cost hundreds of dollars an hour to run in some cases, and you have to walk them into these extremely remote areas. And it's the cost of doing this is running about $10,000 per kilometer. And there's hundreds of thousands of kilometers. So it's not feasible to do everywhere. So we're falling back to these very intensive measures, trying to do things to recover the species. So it's a very difficult situation. Now, the real challenge that we have, back up to the top, the real challenge that we have is that because we are dealing with a species that ranges at a very large scale, the home range of a single caribou is hundreds of square kilometers, talking about distributions that cover the entire continent or the northern part of the continent, obviously. And almost all of the research that we have done has been based on observational studies. So it's basically infeasible to do randomized controlled trials at this kind of scale. So all of our information is coming from these observational studies. Now we're in the position of trying these more intensive interventions. And that means that we need to be able to estimate the benefit. As I said, these actions are very expensive, and we really need to have a good estimate of what their benefit is. And so those of you who have taken Felix's course when that was being offered in connection with the BayesiaLab conference, those of you who've read the Pearl's Book of Why, Causality, the alarm bells are starting to go off for you at this point because you're saying, aha, observational information. We need to know we need to know the effectiveness of our interventions from observational data. And through interventions, we're changing the data generating process. So this is certainly a textbook case for some kind of causal analysis. And we know that causal approaches have been taking hold in some other disciplines that face similar problems to ones that I have stated. So things like epidemiology, also where you can't do any kind of intervention or any kind of experiment, have picked up on these methods, econometrics, et cetera, but they really haven't taken hold in my discipline. And so what I've been trying to do is advocate for these approaches. And so along with my colleagues who I introduced at the beginning of the talk, we're preparing a paper on causal modeling using the caribou system as an example. And we're planning on submitting that for publication just to get the word out and basically just trying to reiterate some of the techniques, apply them in an ecological context, show how they can be used to improve inferences, and then giving some recommendations on how we can move things going forward. But before getting into that, I just wanted to talk about how we've been doing things more commonly in the past. And this, of course, every discipline has their techniques, and this is probably common to what many of you face in your disciplines. But what we settled on is some sort of generalized linear model selection approach. So the idea is to come up with, say, buckets of predictor variables that we would consider to be biologically plausible candidate models. And then we select from those various models using some kind of information theoretic approach, and then report on those supported models in our results sections, and then speculate on the causes in our discussion sections. And whenever I see that, ringing in my mind is always, of course, this famous quote from Causality, basically talking about how we're putting all of our effort into increasingly complex statistical approaches to generate our associations in these complex systems. Then when we actually get to the causal inference, we basically fall back on frankly, a little bit of hand waving in our discussion sections. And I think all researchers realize that's going on. And certainly when I was in grad school, this particular paper was required reading for us. And it's basically talking about how our discipline is far too reliant on inductive and retroductive methods and calling for a much stronger hypodeductive approach to the way we're gaining reliable knowledge, as the title says. The problem with that, of course, is that you can't, in 30 years since this paper was published, we haven't made much progress in that. And the reason is because those kinds of hypodeductive, that kind of experimental approach is infeasible. So we really need to have another way of doing things. And this paper was published before Pearl's book, before things started to roll on this. So now the tools are available, but I really feel that our particular discipline is falling behind in applying these things. So that's why trying to be an advocate for this. And the light really went on for me when I took Felix's course back in the day, and I realized there's something to this. So for several years, I've been looking for ways to apply it to the current situation. Now, the real danger here, the reason why it's super important is that, as I said, we do a lot of causal speculation in our discussion sections, but when we're talking about conservation planning and talking about intervening in these systems to improve our inferences, causal speculation in our discussion sections often very quickly become causal assumptions in our conservation planning. People who are in charge of actually trying to manage these populations read those discussion sections and say, look at this, we have evidence for X, Y, or Z. But really what we have evidence for are the associations and then some speculation on the causes. So what happens is the speculations very quickly get baked into our conservation planning, and that can lead us astray in a couple of ways. And so what we want to do is make sure that we're setting this up properly by reasoning from theory to data rather than from the other way around, from data to theory. Now, of course, you never completely reason from data to theory. Even just the choice of what variables you include in your analyses obviously has some theoretical foundation. So it's a matter of degrees. But I think the point is to load up the front end of our process with this idea of reasoning more clearly from theory to data. And even to the book of why, the first illustration in that book is this very nice workflow. I call it the causal model workflow, where this is really about talking about taking our assumptions and developing an explicit causal model and moving that to the left, basically, in the workflow compared to what we usually do, which is collect a lot of data, do our model selection process, and then talk about the causal model at the end, basically. And the key to that, of course, is the directed acyclic graph. And using BayesiaLab, for instance, you can very quickly, even without data, just put together very quickly a nice causal DAG that explains the system. So this is how I have captured the system that I presented in that nice illustration. And so in this, we have climate at the top, obviously, and that is driving some changes in distribution of fire and also forestry. And what I mean by that is that as you go north, forests become less productive. And when they become less productive, they become less economic to cut. So the colder the area, the less forestry that happens. It eventually just stops as you move north in Canada. Both of those are driving some change in the distribution of our suitable primary prey habitat. And then that habitat, as I said, it makes lots of nice young green vegetation, which increases populations of moose, deer, and elk. Predators move in to take advantage of those moose, deer, and elk. And then our caribou populations decline as a result. And then we have this linear feature component, which is providing some additional habitat, but is also driving the predator-prey system. So here we have a representation of the data generating process. And you can see that there's different causal structures here. There's causal chains, and there's potential confounding that's happening in here. So it's really important to take this, obviously, to the next step of causal identification. I'm not going to go into the details of that. Many of you are familiar, and if not, you can look at the primary literature on that. But the important thing is here that this is a completely different representation then say representing it as a GLM, which would be something like this, where just like a way that's similar to a naive Bayes network, where we assume that all of these variables are conditionally independent. Now, we may be looking for collinearity. We often in a GLM, obviously, you would screen for collinearity. Some of these might drop out. Some data selection process would have some of these drop out. But the point is that this is a very different structure than what we think the actual data generating process looks like. And so the important thing that we're trying to get across is that analyzing your data like this, when in fact you think that the actual data generating process is this, can lead you astray. So this is where I start to look at some of the evidence in some of the current literature. And what we wanted to do was look at some recent papers to understand how we may be led astray by disconnect between what we think the data generating process is and how we're actually analyzing the data. And the first thing is around confounding bias. So I think I've talked about this at some point as well, but going back to this blue paper here, which was the recovery strategy that the federal Canadian government put together to try to recover boreal caribou, it was built off a very simple correlation, which was the amount of total disturbance along the x-axis. So this would be fire plus all the things that we do to create disturbances on the land base, mostly forestry and roads, et cetera. And then the y-axis, it's called mean recruitment. This is basically a measure of the productivity in our caribou populations. Each one of those dots is a different population from across the country. And so all this demonstrates really is that the more disturbance we have on the landscape, the poorer caribou do. So we have this inverse relationship, this negative relationship. And so what the recovery strategy said was, okay, we're just going to pick 35% disturbance, and we're going to say that's what we want everyone to manage to. And as long as you reduce the amount of disturbance on the land base to less than that, we actually think the caribou are going to do okay. So it was a management recommendation that involved an intervention to change the amount of disturbance on the landscape under the assumption that we could just push those dots up to the left based on this simple correlation. But there was no development of the DAG, there was no testing for confounding, et cetera, no diagnosis in there. And that's obviously what we think to be a huge problem. I wanted to go back here. I realized I should have talked a little bit on the inference side down here. I wanted to point out that when we're talking about intervening in the system, there's specific areas where we can intervene. What I've circled in the DAG are the places where we can have some sort of management influence. So you can see we can change the distribution and the abundance of forestry. We can change our land management from that perspective. We can also increase hunting on primary prey. So make the hunting seasons more liberal on moose, deer, and elk and reduce those animals. We can also, much more controversially, obviously, but it does happen, is increase hunting on predators. And that could be handing out more permits to allow people to shoot them if they want, or even to the extreme measure, which has been used in the past, actually hiring people to go out and remove wolf packs. But that obviously is a very controversial move. And we can do, as I showed in that slide showing how we were tearing up the landscape, we can try to implement some sort of process of restoring those linear features. So you can see how we intervene in these different places. And of course, if you want to know how, say, changing your forest management is going to ultimately affect your caribou population trend, it is super important to do the causal identification and adjustment on this DAG to understand what that independent effect is going to be. And BayesiaLab has some tools to help us with identifying those paths. This is a fairly simple DAG, so it's pretty clear what those paths are. But for instance, when we're looking at the relationship between forestry and the caribou population trend, there's one direct path, causal chain through habitat, primary prey density, predator density through to caribou populations. But there's also two non-causal paths, one coming back through climate at around, and the other that is up through this linear density And those are non-causal because there are arrows pointing in the opposite direction. They still provide this backdoor opportunity for biasing our estimates of the effect of forestry on caribou populations unless we condition properly on the right set of variables to control for that. And of course, we also know from this chain from forestry through to caribou population trend what we absolutely should not be controlling for. So if we want to know the independent effect of forestry on caribou population trend, we certainly can't do that in a place where we are also intervening in some way on that primary prey density population or on the predator density. So it's really important to do that upfront work to identify this, to generate those unbiased estimates of the effect of these management actions on the outcomes. Okay, so I'll go back to where I was on this confounding slide. So with that background then, and knowing that what they've really done here is just basically use a synthetic variable where they combined fire and anthropogenic, what we call anthropogenic disturbance. That's all the stuff that we do to the land base, combining those into a single synthetic variable and just correlating it with the outcome and then setting management actions based on that. And the second paper that just came out earlier this year, which really, really encouraged me to be a little more formal about this and try to get some of these ideas into the published literature, is they actually made the explicit link between science and policy by taking this, essentially this univariate relationship and actually making predictions about what we would expect to see in terms of caribou trend if we made those changes to the habitat through restoration. But as I said, without a proper analysis of a DAG that everyone agrees with, there could be some significant biases that could have some significant effects on the likelihood that we would be successful in that. And then this third paper took it one step farther by actually using counterfactual reasoning. So in Pearl's books, talks about the ladder of causation with intervention and counterfactuals at the top. They actually use this fairly straightforward correlation in counterfactual reasoning to predict what the trend in caribou populations would be had there been no anthropogenic disturbance on the landscape at all. And so clearly these papers are moving up the ladder of causation, but at the same time, not applying the causal reasoning to make sure that we're doing our best to minimize the biases in that causal identification. And in our DAG, of course, we talk about climate effects. And so what we did is a very quick analysis to determine what the likelihood is that this climate effect is actually being seen in the data. So map on the right-hand side is a map of a north-south slice of the caribou distribution. The city of Edmonton is down at the bottom and it moves up to Arctic tidewater at the north. Woodland caribou are distributed pretty much right along this gradient. The more things are colored up indicates that there's more disturbance from fire and forestry, et cetera. So you can see that as you move north, it becomes a lot sparser. And that's because the environment is less productive and there's a lot fewer people down as you move north as well. And there is quite a climatic gradient. So if you're down near Edmonton, this range that's just off to the west, that the average January temperature in that range is -9 degrees Celsius, uncomfortably cold. By the time you get to the top of the range at Arctic tidewater, the average January temperature is -29. So you move from uncomfortably cold to really cold. And so that has all kinds of ecological effects in terms of predator prey that you would expect in the north compared to the south, how many people you expect in the north and the south, and also the productivity of those environments. So just looking at the data, we were able to correlate just as they would predict that there is this relationship. On the Y here is the productivity of our caribou populations. And we do see that as the amount of landscape disturbance increases, the productivity goes down. So we certainly agree with their conclusion on that. Secondarily to that, there is this phenomenon that as you move north, you also have less of this disturbance on the land base. And finally, as you move north, you also have caribou doing much better in the north than they do in the south. So the question then becomes okay, is it due to the anthropogenic disturbance going down, or is that due to the fact that caribou are just happier at northern reaches of the study area for other reasons? Perhaps because there's no deer up there, because it's too cold, there's just a few moose and there's not very many wolves. And so they actually are doing much better because there's fewer predators and prey in that, other prey in that environment. So in the perfect world, of course, what I would like to do is load this all into BayesiaLab and take a look at use that as my platform for understanding some of these interactions, but I don't have a lot of data points. So I can't do this. I have to drop out of nonlinear land and drop into linear land on this, do the actual calculation. So I just did path analysis. Of course, path analyses have been around for 100 years, going back to civil rights guinea pigs. And what I did is took the published model, took the data that has been published. They actually distinguished anthropogenic disturbance from fire. And these are the beta coefficients. And you can see based on this analysis that certainly an independent effect of anthropogenic disturbance on caribou survivorship and recruitment. So the population productivity, and it's negative. And the coefficient is about twice that of fire. So fire also negatively affects caribou. Anthropogenic affects caribou as well. And the effect of anthropogenic is about twice what it is for fire. But just by adding this confounding variable latitude to represent climate, then we see a very negative relationship that's evident from the map that as you go north, you get a lot less disturbance. There's actually a positive relationship with fire. So as you move north, the fires get bigger. And I think that's mostly because there's just a lot more forest. I'll just blow that up for you. There's a lot more forest. And I know it's a little fuzzy, but there's a lot more forest and also a lot less firefighting. You get some very large fires in the north. And then again, this positive relationship between latitude and caribou. Caribou are doing better farther north. And it's changed those beta coefficients. So then the effect between anthropogenic disturbance and recruitment, caribou recruitment productivity is half of what it is if you don't include that confounding variable. So if we imagine an intervention on this anthropogenic variable, severs the incoming link, leaving the only direct link between anthropogenic disturbance and caribou productivity. And we end up with an effect that's half of what it is in the published literature. So pretty important distinction that has some important management implications if we're trying to estimate how much do we have to do before we can recover these populations. And what this suggests is that you actually have to work harder you actually have to restore more if you want to see some response in that caribou population, but also that is conditional on where you are in that north-south situation, which is completely missed if you don't take a look at that variable. So just a simple example, but pretty important. Now, one of the things that I really miss when I just do a path analysis is I get these nice diagrams, but it's all very abstract in the sense that you can look at the beta coefficients and look at their relative value, but it's hard to figure out what that means for the whole system. And so I did drop into BayesiaLab to basically recreate that and build a very simple model based on those four variables: latitude, fire, anthropogenic disturbance, and recruitment. Path analyses are all based on all the standardized variants. So what I did is I just used the linear equations. So populate those three, basically populate the CPTs by using these linear equations, including error terms that are derived from the R squareds. And then, so I have basically this Bayesian network built off the standardized linear equations. And then I can also add nodes that do the back calculation to the original variance. So once I do that, now I have my interactive engine that I can use to simulate interventions by saying, okay, what if we were to do some sort of intervention to reduce the amount of disturbance? What would be the expected effect on recruitment? So I can do those kind of interactive what if scenarios that we like to do when we're playing with our networks and looking at the monitors. And the other advantage is that we also get to use the full suite of diagnostic tools in BayesiaLab. So this is the total effects graph, a little bit of nonlinearity here. because I've done this back calculation. So we can see that this is total effects, not direct effects, but as you increase the amount of landscape disturbance, there's certainly a very strong decline in the performance of that caribou population. And you can see how that compares with performance at different latitudes and also levels of fire. So you can see that certainly human impact is still the most significant here, but there are interactions here with these other variables. Okay. That's issue number 1. Just checking my time here. Like it's good. The other piece that I wanted to talk about here is over control bias. So I'm just going to dip into yet another paper published last year in the Proceedings of the National Academy of Sciences. So a fairly high profile paper. And what they did is they took a look at all the different population interventions that we've been conducting on caribou over the past few years. And treatments, you'll recognize them. So the maternity penning, that's where we put the animals and let them calve inside an enclosed area. Wolf removal, moose removal. And also the other one here is translocations. And so this is where you actually take animals from healthy populations and put them in another population, which is not so healthy. And so what this group of researchers did was take all of those different, all the places where those different activities had happened, and then assign a post hoc control to each one of those and analyze it as an ANOVA. And then they said that whole habitat thing is important as well. So we're going to include that as a covariate. So they did an ANCOVA actually. And what they found is when they added in this forest component, this habitat change component, it wasn't really adding anything to their model. And they concluded, oh, I guess it isn't all that important. The really important thing are all these things that we're doing on the direct population intervention side. And that was immediately refuted in another paper that shot at the paper for a couple of reasons. One of the main reasons, and I agree with this, is they felt that the ANCOVA design was inappropriate. And I agree with that because it wasn't really a randomized controlled trial. They didn't assign those treatments. He included in the study, the areas had to be treated, and then they picked post hoc control areas that kind of matched up with those treatments. So now you're thinking, for those of you who are familiar with this stuff, non-selection, they were highly selective in what they chose. Now we're talking about endogenous selection bias. There's some opportunity for that as well. So they did complain about that. But I think one of the most important things is they were saying, you're completely ignoring habitat. There's no way that habitat is not having an effect here. You really missed the most important effect. And we can see how that could happen if we remember our DAG again. So just reminding you, this is what it looks like. And what they did in that study, of course, is they looked statistically at the effect of intervening on this variable. Translocation is actually directly intervening on the outcome variable. And so if we think about something like moose, looking at the effect of moose, the intervention on the moose population, say reducing moose, if you're going to intervene on this variable, the moose density, what you're doing, of course, is severing the incoming link from the suitable primary prey habitat, which is the variable that they included in their design, in their ANCOVA design. So by analyzing the intervention around moose, they severed the only causal link to caribou population trend. And so we wouldn't expect them to find a relationship with habitat. And the same goes for interventions on predator density and even on their outcome variable. So in effect, what they were doing was a kind of over control bias where they were intervening on these intermediate nodes in the causal chain, which interrupted the information flow from the habitat variable. I think intuitively they know this. So I think everybody understands what the data generating process looks like. But when it came to the analysis, they again reverted more to this kind of approach where you could see that if you were analyzing it like this, not recognizing the causal chain structure in that, you could miss that effect in terms of the stats. And I think that's what they did. So a couple of cautionary tales on this in terms of what's happening in the current literature. Back out of this. Founding bias, over control bias. I also raised the specter of endogenous selection bias. So all of those things happening, fairly high profile papers that have come out in the past year. all of these papers are getting reported in the popular press as well. So it's not just the nerds who are debating these things. It's also finding its way into newspapers because it's really becoming a significant issue in Canada. There's so much effort going into this, to the whole aspect of caribou recovery, because it's so important. Species is also very important to Canada's Indigenous populations. So they have hunted these animals for thousands of years. They're declining on the landscape. It has implications for their constitutional rights to gain their living off the land base. And so quite rightfully, they're looking to the Canadian government saying, what are you going to do about this? You've got to improve things for us. And so it's really a highly political issue. And as I said, we have yet to figure things out, but we're really just trying to equip people with the tools to make some better inferences, given the fact that all of our information is currently coming from these observational studies. So I just wanted to finish up with talking about some of the lessons that we're trying to get across. And we're really expressing this as a bit of a cautionary tale. So first up, obviously, if our data generating process looks like this, please don't analyze it like this. And so even if we do talk about this around the table, talk about the data generating process, if we fall back to our general linearized models, that we're going to make some errors when we're in terms of where we're conditioning and not conditioning on various variables. The other piece here is that we do seem to have this over-reliance on this idea of parsimony, and this idea that if we are explaining the most variance in the fewest number of variables, then there must be some causal information in that. And so it's really an argument about getting away from that and not just making post hoc arguments around the causality, but moving that up in our process. So strengthening our reasoning from theory to data rather than the other way around. And just emphasizing the critical role of the causal modeling workflow, and particularly when forecasting management actions based on observational data. I certainly have analyzed lots of systems that are perfectly appropriate to use, say, a more naive, something that's more familiar in terms of a naive Bayesian network structure. That's fine. But if we are actually going to understand the implications around our interventions from these observational studies, it's super important to really key in on that data generating process. Some of this is probably a review for many of you. These conferences, we tend to focus a lot on kind of the big data aspects of this. I work in a place where we really need to bring some stronger theory, I feel, to some situations where you have much smaller data sets. And so I'm always trying to the envelope on applying some of these pieces. So thanks very much. I'm happy to take any questions.